Hey guys, last time we saw why we need a battery management system and what it does. This time we will see what is a BMS made of and how does it work. So, without wasting any time, buckle up guys, let's go for a ride. A battery management system is made up of many hardware and software functional blocks which has cutoff MOSFETs, fuel gauge monitor, cell voltage monitor or cell balancing circuit, real-time clock, and temperature monitor system. Now let's take a look at the purpose and the technology behind each block. First is the cutoff FETs. These are basically transistors, mostly MOSFETs are used. MOSFETs are nothing but control switches. These are used for connection and isolation of the battery pack between load and charger. Microcontroller unit of the BMS measures cell voltage and current in real time, and based on that, it switches the FETs. These can be configured in two types. Here, it has single connection to the charger and load. In the electric vehicle, we can say it's motor controller or motor. Second diagram has two different connections for the charger and load. Generally, first configuration is used in the BMS because it reduces the hardware where just one bus controls the charging and discharging. Well, how does this MOSFET work? Initially, both MOSFETs are turned off. When a charger is connected, the current is not flowing because FETs are off. BMS senses the voltage at the input and then it turns on the C FET, which lets the battery get charged. If the voltage at the input pin is not present, then BMS determines that motor is connected. Then it turns on the D FET. Next block is fuel gauge or current monitor. This block keeps the track of the charge coming in and going out of the battery pack. Charge is the product of current and time. For measuring the current, a current sense amplifier and a MCU which has an analog to digital converter is used. A very low value current sense resistor is connected in series with the battery line. Voltage drop across this resistor is measured by this amplifier and then it amplifies the signal and delivers it to the ADC of the microcontroller. The microcontroller measures that voltage and calculates the charge according to the time. The discharging and charging current is sensed by the direction of the current. If the current is going out of the battery, then battery is discharging, and if the current is coming inside the battery, that means battery is charging. Or there are certain fuel gauge ICs which are available in the market which takes care of the SOC estimation of the battery. Many times, using a fuel gauge IC adds additional cost to the BMS design when the load current is changing continuously, as in electric vehicle case. Using a shunt resistor is always the best option. This configuration also helps for overcurrent protection. When current rises above safety level, the fuel gauge circuit senses it and gives the signal to turn off the D FET or C FET. Next comes the voltage monitoring or cell balancing circuit. Generally, lithium-ion batteries are used in electric vehicles. The voltage of a lithium-ion cell ranges from 2.5 volts to 4.2 volts, and it depends on the chemistry. As we saw last time, operating the battery outside the voltage range significantly reduces the lifetime of the cell. Even if the cells are created by the same manufacturer and in the same lot, physical properties such as internal resistance, the nominal voltage, and temperature imbalance will slightly differ from each other. While charging and discharging, not every cell behaves the same. While charging, if the battery pack has a weaker cell than an average cell, this would result in the weaker cell to reach out its limit first, while rest of the cells are still charging. So this weaker cell heats up and its lifespan decays. On the other hand, a weaker cell discharges faster than the rest of the cells. The weaker cell trips the discharge limit first, leaving the rest of the cells with some charge remaining inside of them. So, this can be overcome by cell balancing. This cell balancing is derived into two parts. First is the passive cell balancing, and second is the active cell balancing. The passive cell balancing is the simplest and cost-effective method. In this, a dummy load like resistor is used to discharge the excess voltage and equalize it with other cells. These resistors are known as bypass resistors. Each cell connected in series in a pack will have its own bypass resistor connected through a switch. While charging, the weaker cell charges very fast, so the MOSFET connected across the weaker cell is turned on. The charge of this cell is removed and dissipated through this resistor. This process minimizes the charging rate of the weaker cell. Whenever charge level of the weaker cell tends to go near to its full capacity, the MOSFET is turned on. So all cells along with weaker cell charge at the same time. But this method is not useful while discharging. The weaker cell may reach to its minimum cutoff voltage earlier than the other cells. However, this balancing technique is cheap and technically easy to implement. But this method is not very efficient because electrical energy is dissipated as heat in the resistors and FETs. Another drawback is that the entire discharge current flows through the MOSFET, which is mostly built into the controller IC. Hence, the discharge current has to be limited to lower value up to the IC's limit, which increases the discharging time. So this configuration of bleeding resistor and MOSFET minimizes the charge discharge rate by slowing the charging and discharging of the weaker cell. Unlike passive balancing, in active balancing, the excess charge from one cell is transferred to another cell, which has low charge to equalize them. So, this can be done by charge storing components like capacitors and inductors. Well, there are so many methods to perform an active cell balancing. Let's discuss the method which is commonly used. The charge shuttles or flying capacitor is the most commonly used method in the active balancing. In this, the capacitors are used to transfer the charge from high voltage cell to low voltage cell. The capacitor is connected through SPDT switches. Initially, the switch connects the capacitor to the cell which has higher voltage, and once the capacitor is charged, then the switch connects it to the cell which has low voltage, and charge from the capacitor flows into the cell. These capacitors are called as flying capacitors. Well, the problem with this method is that the charge can be transferred only between adjacent cells. But still, it is better than passive cell balancing. Just like this, there are many active cell balancing techniques which are out of the scope of this video. Next important parameter is temperature monitoring. Lithium-ion batteries provide a lot of current while maintaining constant voltage, which can lead to a thermal runaway condition that causes the battery to catch fire. The construction of a battery is highly volatile. Well, this temperature measurement is not just for safety. It can also suggest if the temperature of the battery is suitable for charging or not. To measure the temperature of this battery, a temperature sensor is used. Generally, the thermistors are used as a temperature sensor. The thermistor is basically a temperature dependent resistor. Whenever there is a change in temperature, the resistance of the thermistor changes, and BMS calculates the temperature rise accordingly. The BMS acts as a logbook to calculate the SOH and other parameters of the battery. So for that purpose, the BMS has to take the data according to time. So it should be working even if the vehicle is not on, but it might consume the excessive power from the battery pack itself. So, to avoid that, a real time clock is integrated with the BMS, which needs very small power and it does our job. So, that's all about the BMS of an electric vehicle. If you think there is something missing, please let me know in the comment section. Hit the like button if you liked this video, subscribe to my channel, and finally, thanks for watching.